So last time we looked at the concept of a power series solving a differential equation. Now we need to look at that a little bit closer. So let's um, dive into this concept of solutions about an ordinary point for a power series. So we've seen the standard second order linear differential equation. In this case, this is specifically homogeneous. Um, this homogeneous can be put into standard form where we divide by the a sub 2 and we get this second order standard form homogeneous linear differential equation. So we're going to talk about solving these differential equations using power series. Now there was a couple of things I talked about before that we really need to dive into. It's when can we come up with a power series solution, what should the center of that power series solution look like, and that revolves around talking about this concept of ordinary and singular points. So this says a point x sub 0 is said to be an ordinary point of the second order differential equation if both p of x and q of x in standard form, so we're talking about these here, are analytic. Okay, at x sub 0. Now what does analytic mean? Analytic means that these functions can be written as a power series in x minus a, where a is the positive radius of convergence, with a positive radius of convergence. So essentially, um, these two functions are functions that can be written as a power series centered at some value a with some radius of convergence. Okay? So a point that's not considered to be ordinary, for which we can't find out where these two functions are analytic, is said to be a singular point. So we're talking about ordinary points and singular points, and it's all about whether or not these functions can be written as a power series centered at some value a. So look at this differential equation down here. Okay? This is in standard form. This is a second order standard form linear homogeneous. Look at the functions p of x and q of x. We talked about this last time, that there are some real common functions that can be written as power series, in which case e to the x and sine x are two of the most common ones that can be written as power series. And they can be written as a power series centered at 0. Now you would need to know all that to be able to realize that these two functions are analytic when x equals 0. Okay? So therefore x equals 0 is an ordinary point for this differential equation. Now that would require you to know which functions can be written as power series, what the center of that power series is, for every single function that could possibly come up here and here. We're going to make it easier on you because we're not going to look at just random functions. We're going to look at specifically polynomials, which finding whether or not it's ordinary or singular is easier to do, but generally right now that's the initial definition of ordinary versus singular. Look at this differential equation here. Also a second order standard form, p of x, e to the x, same as before. Q of x is now log x. Now both of these can be written as power series. However, they cannot be written as a power series centered at 0. So therefore, this differential equation has a singular point when x equals 0, essentially because of the log x being discontinuous there, and therefore it doesn't have a power series for which x equals 0 will work. Again, that will require you to know the power series and the center of the power series for each one. So you can see how this could be quite difficult, but technically, if it's an ordinary point versus singular point, regardless of how easy or how hard it is to find, everything we talk about moving forward would relate to stuff like this. Now look at these differential equations. These look like nothing that we've been able to solve up to this point, because if you think about the two types we've solved constant coefficient and we solved Cauchy-Euler. This and this both are neither of those. And so ultimately we're going to try and look at things that are not looking like this, but maybe not as difficult as maybe these are as well. So if we primarily focus on differential equations that don't just have random functions as the coefficients. So we're talking about this a sub 2 of x, y double prime plus a sub 1 of x, y prime plus a sub 0 of x, y equals 0. These linear second orders, where we're not looking at ones where these functions are just completely random functions. Because that, again, could be fairly difficult to start to realize what's ordinary, what's singular, which ones can be written as power series, what's the center of those power series. Instead, we'll make it a little bit easier and narrow it down and say we're only going to look at differential equations where these coefficients are polynomial coefficients. Okay? So not e to the x, sine x, log x, just straight polynomials. Now, if these are polynomials, when I put it in standard form, y double prime plus p of x, y prime plus q of x, y equals 0, then what happens is p of x would be a sub 1 divided by a sub 2, and q of x would be a sub 0 divided by a sub 2. Well, if a1, a2, and a0, if they're all polynomials, then p of x is a polynomial divided by a polynomial, which makes p of x rational. And the same thing for q of x. They're rational. Now, to determine if a rational function is analytic and therefore has a singular point, it's actually really easy to do. It's all about looking at whether or not the function exists. And if it's a rational function, a fractional function, it exists as long as its denominator isn't 0. So the denominator for both of these is a sub 2. So p of x and q of x are analytic as long as a sub 2 doesn't equal 0. And it'll be singular, which basically will tell me when we're going to have an ordinary point. And it'll be singular when a sub 2 does equal 0. So if we just focus on polynomial coefficients, it's very easy to find ordinary and singular points because it's easy to figure out whether or not these two functions are analytic at a given value. So let's look at a couple of these examples. Let's look at this example first. In this example, p of x would end up being 2x over x squared minus 1. Q of x would be 6 over x squared minus 1. In either case, the denominator, x cannot equal plus and minus 1. So that tells me that these two functions would be analytic and therefore have ordinary points as long as I don't choose these two x values. So all x except x equals plus and minus 1 are considered to be ordinary, and x equals plus and minus 1 are singular points for this differential equation. So real simple. Okay. If I look at this differential equation, which is a Cauchy-Euler, which we really wouldn't be doing power series solutions for this, because we have other ways of doing it which are much simpler. This is only kind of something we would use if we had to. But nonetheless, if you just look at this Cauchy-Euler one, the leading coefficient is ax squared. That's the a sub 2. That would equal 0 when x equals 0. So essentially x equals 0 is singular. All others are ordinary. And now look at this one here. This leading coefficient, which would be the denominator if I divided for my p of x and q of x. That's never equal to 0 because x squared plus 1 never equals 0 if we're talking about real functions. If we're talking about imaginary, we can do that. We can say plus and minus I would be our singular, and all others would be ordinary. Okay, that's terrible, but you get the point. So determining singular and ordinary, determining if functions are analytic when we're working with polynomial coefficients is actually pretty It's not as bad as the initial definition made it seem, where we had to remember all the functions that can be written as power series and what the centers of those power series are. Okay? Now let's take a quick look before I pull off this slide. Let's look at these differential equations here. The first one and the third one. Neither of those are types of differential equations we've been able to solve up to this point. They aren't Cauchy-Euler. They aren't constant coefficients. So if we're able to use power series to solve these two, then we're able to find a way to solve them that we really haven't looked at before. Up to this point, these two are basically not solvable. And you might look at them and go, well, they look like Cauchy-Euler, just kind of off. This +1 and this -1 basically are the reason why neither of these are Cauchy-Euler. If it was just x squared y double prime plus 2x y prime plus 6y, yeah, it's this setup. But x squared -1 or x squared +1 throws the whole thing off. So neither of these are Cauchy-Euler. But we're going to solve these using power series. This one, which is Cauchy-Euler, there's no sense to even bother with all this power series business. We can solve that any way we want using what we've learned before with the auxiliary equation, etc. Okay, so here's the big theorem that's going to basically tell us how we can do this and why we can do this, or I should say when we can do this. So it's this existence of a power series solution. When is a power series solution going to exist for a differential equation? So it says, if x equals x sub 0 is an ordinary point for a second order differential equation. So we're talking about second order differential equations here, and we're talking about ordinary points. We can always, this is a big one, always find two linear independent solutions in the form of a power series centered at x sub 0. Always. It doesn't say what kind of second order linear differential equation that we can work with. It's not giving us saying it's got to be constant coefficients, it's got to have polynomial coefficients even. It technically could have any coefficients we want as long as it fits the linear. I really should put in there second order linear. Okay. But we can always find two linear independent solutions as long as this power series itself is centered, and this is right here is the center of the power series, as long as the power series is centered at the ordinary point. So that's why ordinary points are so important, being able to determine if we have an ordinary point. Now, this last piece, a series solution converges, at least for absolute value of x minus x sub 0 is less than r, where r is the distance from x sub 0 to the closest singular point. All that's telling you is that this function, which is their power series function that's solving the differential equation, can only solve the differential equation if it exists. And it's only going to exist in its interval of convergence. This is the way we looked at finding the interval of convergence, with the radius of convergence being r, x sub 0 being the center. So it's just telling you that you need to make sure that the power series itself is going to exist, and you only work with the values for which the power series exists, which is really the case all semester. Whenever we find a solution to a differential equation, we're trying to find the solution, and that solution has to exist, so we have to stay into that functions domain for which that function will solve the differential equation. We haven't really looked at that a ton. We've talked about it in the beginning of the semester, but that's all this is saying. So we're not going to dive too far into this. It's more or less just coming up with a series solution. So again, the solution of the form here, same thing. I just replaced my x sub 0 with a. It's all the same. Is said to be a solution about an ordinary point x sub 0. Okay, this is a solution for the differential equation about or centered at an ordinary point, based off of this, radius of convergence and looking at the series solutions. So this is just reiterating what we've already said, but it's just talking about what we can call this. We can call this a solution centered around an ordinary point. So the way we're going to do this, we've already looked at. We've already done examples of this. The concept is We're going to look at what the solution should look like. We're going to create a power series setup based off of what we just learned that as long as it's centered at an ordinary point, we'll be able to find a solution. So we know the basic form of the solution. We're just going to find the specific solution that's going to work. So once we have an idea of what the form of the solution should look like, we're then going to plug it into the differential equation. In order to do that, we sometimes have to take the derivative and even the second derivative. And then once we plug that form in, through our computations, we'll learn exactly what the specifics of that power series would have to look like in order to solve the very specific differential equation. So we're going to do this for homogeneous differential equations. But we could do this also then for non-homogeneous differential equations because we have variation of parameters. The variation of parameters will allow us to then say, all right, we have two solutions. They happen to be power series. And then once we have those two power series solutions, that's our y1 and our y2. We then would have to go ahead and find u1 and u2 through the whole variation parameter setup. And we could extend all this to the non-homogeneous. But we have to be good at solving the homogeneous ones first before we can even get into that. And the good news is we're not going to go that far with this. We'll stick to just the homogeneous, and then we're not going to dive into the non-homogeneous. But technically, we could get into this by doing, the variation of parameters and looking at, what would give us the solution here. So we're going to just stick to this right here, finding the solution to the homogeneous one, the general solution, c1y1 plus c2y2. Oftentimes c1 will be written as c sub 0 and c2 would be written as c sub 1. It doesn't really matter, it's completely arbitrary. But y1 and y2 would be the two functions that solve the differential equation, and those two functions are going to end up being power series. So we're going to look at what power series can solve the differential equation. In this case, this one's centered at 0, but you're not always going to be able to center it at 0. You got to center it at an ordinary point. So if 0 is a singular point, you can't center your power series at 0. But if we can center the power series at 0, we're ultimately going to try and do that because computationally, it's less writing that you have to do. Right? So here we go. Let's look at this one. So here's the power series. Here's the differential equation we're looking at solving. It looks like a fairly simple differential equation. But this is a differential equation that we would not be able to solve without looking at this power series solution. It's not one of the two higher order differential equations we've dealt with so far. It is not constant coefficient. It is not Cauchy-Euler. Even if you try and multiply through by x, or x squared, or whatever, it's not going to work. So what seems fairly simple is actually not as simple as it looks to be able to solve. But we can use power series to solve this because that last theorem said you will always be able to find two power series solutions to a second order linear differential equation as long as those power series are centered around an ordinary point. So look at the leading coefficient. The leading coefficient here is a 1. That's the a sub 2. That is never going to be 0. So all x are ordinary points. Right? So, oh God, that was terrible. Let's try that again. All x are ordinary points. So we could find a power series solution. We can assume that this is the solution, which is a power series centered at 0. 0 is an ordinary point, so because all x's are ordinary points. So all values, all x sub 0, I should say x sub 0, not x. All x sub 0 are ordinary points. So in this case, right, let's keep it easy on ourselves. Let's center our power series at 0. If you don't want to center at 0, technically you could center it anywhere you want because everything's an ordinary point. I could say, let's find a solution of the form n equals 0 to infinity of c sub n x minus square root of 2 to the n. And that's going to be what my power series is going to look like as a solution. But I'd have to keep writing x minus square root of 2 over and over and over again. Every time I see an x, it's going to be x minus the square root of 2 to the n minus 1 to the n minus 2. And I really don't want to do that. So we are going to center at 0. So here's the solution, but that's not really a power series. That's just a form of a power series. We got to figure out which specific power series will solve this. The derivative of that would look like this. Remember, bump the index up by 1. The rest is power rule. Power comes out to the front. New power is 1 less. Take the derivative again. Index bumps up by 1 again. Power comes out again. New power is 1 less again. We only got to go to second derivative because it's second order. So y double prime plus xy would turn into second derivative plus x times the original function. And this should equal 0, right? Because we're talking about homogeneous. So then what I need to do is I need to push this x into this series. If I push this x into the series, this is x to the first, this is x to the n, so that becomes x to the n plus 1. Still, that whole thing is the left-hand side. That's this, okay? And it should equal 0. Next step is now we got to put these two series together as one. So what do we got to do? We got to make these two powers match up to become exactly the same. We'll do that by substituting in k, and we have to make the two indices match up as well. Okay, so what we're going to do is we're going to say let's let k equal n minus 2. So n ends up being k plus 2. And here k is going to equal n plus 1. So n is going to equal k minus 1. So this series can turn into the sum of k equals 0 to infinity. Again, because if n is 2, then that'll tell me what k is. C sub k plus 2 times k plus 2 times k plus 2 minus 1. Again, I'm just plugging n as k plus 2 in here, here, and here. So k plus 2 minus 1 would be k plus 1, x to the k, plus the sum of, well, if n is 0, that would make k now 1, c sub k minus 1, x to the k. Okay. All right. So now our powers are matched up. Next thing we want to do is deal with these indices. They're not the same. It's always easier to bump your index up than to bump it down. So we're going to move this index up to 1. The way we do that is we run one term out of this series. The first term, which would be the k equals 0 term. I'm going to plug k equals 0 in, and that'll come out of the series, and then the rest of the series should now start at 1. So I will have k is 0. I would get c sub 2 times 2 times 1 x to the 0. Now I'll still have the rest of the series still to go, which would then be now at 1. Still, the series doesn't change. It's still c sub k plus 2, k plus 2, k plus 1, x to the k. And this other series here is still k equals 1 to infinity, c sub k minus 1, x sub k. So now I have everything I need. I got the indices matched up. I get the powers matched up. So that I can condense these two into one series. So this thing right here, I'll just rewrite this a little bit. It's going to be 2 c sub 2 x to the 0 plus, now this whole thing is going to start at 1 because both of them start at 1. Then I'll have this coefficient plus this coefficient. So it'll be c sub k plus 2 times k plus 2 times k plus 1 plus c sub k minus 1 x to the k equals 0. And here's where the equals 0 part is really big. This is homogeneous equals 0. This on this side of the equation over here, you have an infinite polynomial. You have some coefficient x to the 0. Then when k equals 1, you're going to have some other coefficient x to the first. Then when k equals 2, some other coefficient x to the second, etc. And it's just going to be something, you know, x to 0 plus something, x to the first plus something, x to the second plus something, x to the third, etc. It's going to keep going, and that equals 0. We talked about this. The only way that could equal 0, or two ways that could equal 0 would be one, is if x itself were 0, okay? But that does nothing for us. Or if every single one of these coefficients here were 0, so there'd be 0, 0, 0, 0, 0, so you have 0 plus 0 plus 0 plus 0, and that should equal 0. So we're looking at the coefficients to be equal to 0. Let's make some space here. There we go. So this coefficient has to equal 0 in front of this one. So that tells me that 2c sub 2 has to equal 0. By default, that means c sub 2 has to equal 0. Or every other coefficient as well has to equal 0. And this is how we're going to create every other coefficient. So that whole thing, for any k, starting at 1, would also have to equal 0. Again, remember, it's for k equals 1, 2, 3, etc. Because that's where k starts. So we'll rewrite this for c sub k plus 2, because that's the bigger one. That would equal negative c sub k minus 1 over, what did I have here? I screwed this up. This is 2, this is 1. This would be k plus 2. This would be k plus 1. And again, using these k's. So what we could say is, all right, well, let's say k equals 1. Well, if k equals 1, we could say that c sub 3 would be negative c sub 0 over 3 times 2. And if k equaled 2, we'd figure out that c sub 4 equals negative c sub 1 over 4 times 3. And if k equaled 3, we figured out that c sub 5 equals negative c sub 2 over 5 times 4. However, c sub 2 equals 0, so actually c sub 5 is going to end up equaling 0. So k equals 4. So k equals 4. We're going to get c sub 6 to be negative c sub 3 over 6 times, what did I say, 6 times 5. However, c sub 3 is c sub 0, so it's going to end up being actually positive c sub 0 because it's negative c sub 3, negative, negative, give me positive. And then I'll have 2 times 3 times 5 times 6. Let's go a couple more. Let's go k equals 5. That'll give me c sub 7, which would be, what about that would be negative c sub 4 over, where are we at here? 7 times 6. But c sub 4 is negative c sub 1, so it would be positive c sub 1 over 3 times 4 times 6 times 7. And last one I'll do is k equals 6 is going to be c sub 8 to equal negative c sub 5 over whatever. I don't have to even worry about that because c sub 5 is 0. This is going to be 0. So you see a kind of pattern developing. And then we got to keep going until we get a pattern. Everyone was asking, how far should I take this? How many times do I got to write this out? you're going to have to write it out till you get a good couple of terms, because you're going to have two solutions. You need enough terms for each solution, and you need to see a pattern. So, you're probably going to have to take it out 4, 5, 6 different terms. Okay, so if you go back and look, you'll see that we found different C sub values, but we never figured out what C sub 0 or C sub 1 would equal. We said C sub 2 equals 0, C sub 3 equals negative C sub 0 over 2 times 3, C sub 4 equals negative C sub 1 over 3 times 4, etc. We never figured out what C sub 0 or C sub 1 equal. So we're just going to call C sub 0 and C sub 1 C sub 0 and C sub 1. We have no idea what else to call them, so that's what they're going to stay. But we did find all these other C values. So we said the solution, y, should have been of the form n equals 0 to infinity of c sub n x to the n. Should have been a power series centered at 0, and that's just a general power series centered at 0. If you were to write it out, it would be c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed plus c sub 4x to the fourth, etc. Okay? So we found that c sub 0 is just c sub 0, and c sub 1 is just c sub 1, but c sub 2 is 0, and c sub 3 is negative c sub 0 over 2 times 3, and c sub 4 is negative c sub 1 over 3 times 4, and c sub 5 is 0, and c sub 6 is positive c sub 0 over 2 times 3 times 5 times 6. And c sub 7 is positive c sub 1 over 3 times 4 times 6 times 7. And c sub 8 is 0, etc. It keeps going. So then if we look at this and we say, all right, well, that's the solution y. But really we could break this up into two different things. There's certain terms have c sub 1s and certain terms have c sub 0s. So if I take all the c sub 0 terms and I start putting those together, and I factor out the c sub 0, I would get 1 minus 1 over 2 times 3 x to the third plus 1 over 2 times 3 times 5 times 6 x to the sixth. The next one will be minus 1 over 2 times 3 times 5 times 6 times 8 times 9, and this should probably be x to the ninth, etc. You can see kind of a pattern developing there, right? And then I take the c sub 1 terms and I pull c sub 1 out. I would then have x minus 1 over 3 times 4 x to the fourth plus 1 over 3 times 4 times 6 times 7 x to the seventh minus something else, and we'll just keep going. I really have a solution that looks like this. Y equals c1y1 plus c2y2. I'm calling them c0 and c1, but who cares what we call them? They're standing for random constants anyway. So this is y1 and this is y2, which are the two solutions to differential equations, and they just happen to be power series solutions. Now we only have the first couple terms of each one of those power series, but those are your two solutions. That's the first solution as a power series, and that's the second solution as a power series. Now we didn't write the solution for y1 in summation notation or y2 in summation notation. I'll show you that in a second. It's not easy to do, but nonetheless, these are the two solutions. And that theorem we talked about said we will always be able to find two power series solutions to the second order linear homogeneous differential equation as long as we center it in an ordinary point. And we did. We said this is the power series and it is centered at an ordinary point because all points were ordinary points. Now if you look at those two solutions we had, which pretty intense, there's a lot to them, the two solutions, there's one issue here. This should be an x. The first couple of terms of each solution look like this. Okay? We only went out to a couple of terms. We didn't really come up with this term, but we could have kept going and gotten that. If you were to condense them into summation notation, this is what they would look like. And you can see that this would generate this, and this would generate this simply by saying, okay, k equals 1, let me plug 1 in, k equals 2, I'll plug 2 in, etc. But getting to here is not an easy thing to do. I'm not going to ask you to do this. Okay? I'm going to ask you to get this far. And if you can get this far, and really you need at least 3 to 4 terms of a series to really tell me that you know what the series is. If you give me just the first 2 terms, that's not good enough. Since I'm not making you do the summation notation, you at least need to give me 3 to 4 terms. I would prefer 4 terms of each of the power series to be able to tell me what the solution is. But I'm not going to ask you to do this. However, when you look up your answers in your book, the book's going to say, here's one answer and here's another answer. So you're going to have to figure out what you have is the same as this. And the only way you can do that is simply by looking at what they have and saying, okay, if I were to plug in 1 and then 2 and then 3 and then 4 into here, would it generate all these terms? Okay. So let's take a look at this bottom one right here. The first piece is x, and you should have had an x here. I said there was a little error on my part. There should be an x there. Then the next term is this one, which would be really the first thing I get when I plug into here, because the first term is actually pulled out. So if I plug 1 into here, I would get -1 to the first, which would be -1, and it's got a negative 1. Here, if I plug 1 into here, it would be x to the 3 times 1 plus 1, which would be 4, which is here. And then this bottom piece would be 3 times 4. If I plugged in 1 here, what you would see is this would be 3 and this would be 4, which means that I just stop at the 3 times 4 because this is already 3 times 4, which is what I would have. And I look at the next term, which would be when k equals 2. I plug 2 into here. That would give me -1 to the second, which would be +1. If I plug 2 into here, this would give me x to the 6 plus 1, which would be 7, so that would be there. K equals 2, so this would be 6 times 7, so I'd have 3 times 4, and then I have to go all the way to the 6 times 7, which I have, so that's my next term, etc., etc., etc. So I'd have to check each one of these to make sure it's giving me what I would have on my paper, which would be this. It's not the best situation, but it's a heck of a lot better than me making you do this for every single one, which could take upwards of hours for you to figure out that pattern to do. So, you're welcome. All right, here's another one. Again, look at it. It's one of the ones I showed you earlier. It's not constant coefficient, it's not Cauchy-Euler. So if we go ahead and try and solve this, the only way we have right now is this whole power series way of doing it. So look at the leading coefficient here. It never equals 0. And since it never equals 0, every x is an ordinary point. Every value is an ordinary point. So I want to center my power series at ordinary points. So how about we center our power series at 0? So we're going to assume that the solution is this power series centered at 0. The derivative would look like this. The second derivative would look like this, for all the same reasons we discussed already. If you have no idea what I'm talking about, rewind the video. I already said it. All right. Anyway, so let's plug all these things in and see what's up. So we got x squared plus 1 times the sum of n equals 2 to infinity of n minus 1, n minus 1, c sub n, x to the n minus 2. because that's the second derivative, plus x times the sum of n equals 1 to infinity of n c sub n x to the n minus 1 minus the sum of n equals 0 to infinity of c sub n x to the n. Again, that should equal 0. So let's start working with this now. We got to try and condense all this. We're going to take this and try and push it in. We're going to take this and try and push it in. The problem is here, this is addition, and that's multiplied by the power series. So this whole power series will have to distribute into there and to there. So this is going to start to get a little long on this one. So we got x squared times the sum of n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2 plus 1 times that, so we got another one of these, n equals 2 to infinity of n minus 1 c sub n x to the n minus 2 plus, now this x got to go multiply into here, so we have the sum of n equals 1 to infinity of n c sub n x to the, if this x goes in, this is now just going to be x to the n, minus the sum of n equals 0 to infinity of c sub n x to the n, which is just this one with nothing else going on it, equals 0. So then what we need to do is try and condense this more. So this x squared has to go in here. So if I push this x squared into here, this now is gone. This minus 2 is gone because I have a plus 2 minus 2. So that'll just be x to the n. I'm not rewriting the whole thing over again. You can see how that's going to happen. All right. Then what do we want to do? We want to try and make this all turn into one series. So we need all the powers to match up, which some of them look like they do already, but not all of them. And then we need the indices to match up, which kind of some of them do, but not all of them. So let's work at the powers first. We'll do the same thing we've done in the past examples. We'll let k equal that power. For that, k equal this power here, k equal this power, and k equal this power. In which case, the only one we have to worry about is n equals k, k equals n, but this one, n would equal k plus 2. So this series turns into the sum of k equals 2 to infinity of k minus 1, c sub k, x to the k, plus this one turns into the sum of k equals, what would that be? If n is 2, k would be 0, k plus 2, that'd be k plus 2 minus 1, so k plus 1, c sub k, x to the k, plus the sum of k equals 1 to infinity of k, c sub k, x to the k, minus the sum of k equals 0 to infinity c sub k, x to the k equals 0. Okay. So now they're all x to the k, but now I need to make the indices match up. So the highest one is this one. So I got to get all these to come up to 2. So that means I got to run 2 terms out of that one. I got to run 1 term out of that one, and I got to run 2 terms out of that one. This should be fun. All right, so 2 terms out of this first one here. Let's see, what are we going to do? The k equals 0 term, which would be 2 times 1 c sub 0 x to the 0. And then the second term would be the k equals 1 term. So if I plug 1 in, I would get 3 times 2 c sub 1 x to the first. Okay. Then I got to run 1 term out of here, which would be the k equals 1 term. So that would be 1 c sub 1 x to the first. And then I got to run 2 terms out of this one, which will be, and they're both going to be subtracted. There's a minus in front of them, so be aware that whatever we pull out is going to be subtracted. So then that's gonna give us what? K equals 0, so minus c sub 0 x to the 0 minus c sub 1 x to the 1. Now, what we have is all of these are now going to be at 2 because of all the terms I pulled out. So then I would have all these different series minus this last one, and they would all be starting at 2. And they'd all be x to the k, x to the k, etc. So in order to put them all together, I got to take this coefficient, this coefficient, this coefficient, and this coefficient, and put them together. But there's a problem there. Ah, I see it. Probably saw it before me. This one right here. N is k plus 2, so this should be k plus 2 right there. But everything else is okay. And that didn't change any of these terms here. Well, it did because if k equals 0, this should be c sub 2. Where was that? That was the two terms. So this should be c sub 2. And k equals 1. This should be c sub 3. I think we're good now. Yeah, okay. Anyway, so this is kind of a mess. Let's clean this up. So what do we have? We're going to have these four coefficients all have to come together. You see there's a lot of c sub k business in here. And then I'm going to have to clean up all this stuff too. You notice they're all either x to the 0 or x to the first. So I think you see right away that these two actually cancel each other out. So what do we got here? We got these two c sub 0 terms. Okay. We're going to clean that up. So what do we have? We're going to have 2c2 minus c0, and that's going to be my x to the 0 coefficient. Then I have 6c3, and that's going to be my x to the first coefficient. Then I'm going to have everything else. Remember, starting at 2, I'm going to have this right here, which is k minus 1 c sub k, plus this one, which is k plus 2 k plus 1 c sub k plus 2, plus the next one is k c sub k minus the last one, which is c sub k. That's all the coefficients, x to the k, and it should equal 0. This is where not having a board is going to be rough. Alright, so I only have limited space here. Alright, well, we can clean this up too. I'm going to go to another slide to do all this. Alright, so this is where we're at. I'm going to have to fix this summation stuff up. If you notice, there's a bunch of c sub k's in here. So I'm going to clean this up. If I put these two together, I have k minus 1 c sub k. Then if I put this one and this one together, if you notice, they both have a k minus 1 and a c sub k. So if I factor out the k minus 1 and the c sub k, I'd be left with a k here. And if this is all gone, I'd be left with a plus 1. Okay? And then I still have this k plus 2, k plus 1, c sub k plus 2, then that whole thing, x to the k equals 0. So that looks a little bit better now. And we still have this stuff transposed down into here. X to the 0, x to the first, plus. Okay. So now we're back to the equals 0 part of this whole thing. So this has to equal 0, this has to equal 0, and every one of these, depending on where k starts, 2 in this case, all have to equal 0. So if 2c2 minus c0 has to equal 0, that tells me that c sub 2 has to equal c sub 0 over 2. So that's one piece. If this has to equal 0, that automatically tells me that c sub 3 has to equal 0. Okay? And then if this whole thing has to equal 0, it's going to tell me that c sub k plus 2 has to equal negative c sub k times k plus 1, k minus 1, which is this, just move to the other side, divided by k plus 2, k plus 1. I can then cancel these two k plus 1s. So that would have to, c sub k plus 2 would have to equal that for k starting at 2, then 3, then 4, etc. Because that's where this starts. So we got C2, we got C3. If you notice, we're going to start with k equals 2, so that's going to tell me c sub 4 equals negative c sub 2 over, or negative c sub 2 times 1 over 4. But since c sub 2 is back here at c sub 0, it's going to be negative c sub 0 over 2 times 4. And when k equals 3, we're going to see that c sub 5 equals negative c sub 3 over, or times, I'm going to keep forgetting this, k minus 1, 2 over 5. But c sub 3 was 0, so that's going to equal 0. Let's go a little bit further. K equals 4. I get c sub 6 to equal negative c sub 4 over, again, I forgot the k minus 1, 3 over, where are we at here? What was it? So 6. But c sub 4 was negative c sub 0, so this will be positive c sub 0 times 3 over 2 times 4 times 6. And you see the next one, k equals 5, is going to give me c sub 7 to be negative c sub 5 times something over something, but c sub 5 is 0, so that's 0. Alright, so now let's go back to what we said. We said our solution was of the form n equals 0 to infinity of c sub n x to the n, which in this case would be c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed plus c sub 4x to the 4th, etc. Notice in this whole process we never figured out what c sub 0 equals, so that's just going to stay c sub 0. We still didn't find what c sub 1 equals, so that's going to stay c sub 1. We did find out that c sub 2 equals c sub 0 over 2. We did find out that c sub 3 equals 0. We did find that c sub 4 equaled negative c sub 0 over 2 times 4. We found out that c sub 5 was 0. We found out that c sub 6 was c sub 0 times 3 over 2 times 4 times 6, x to the 6th, and we kept going. So much like we've done with the other stuff, we're going to do the same. We're going to separate, notice all these c sub 0 terms. I'm going to factor a c sub 0 out, and I'm going to get 1 plus 1/2 x squared minus 1 over 2 times 4x to the 4th plus 3 over 2 times 4 times 6 x to the 6th minus, etc. You see there's a pattern, it's going to keep going. And then if you look at the c sub 1, there's actually only one term with a c sub 1 in it. so I'm separating it, but it's only c sub 1x. Nothing else is going to have a c sub 1 in it. We got all these ones that are 0, so they're all just going to go away. But we still do have two solutions. Here's one solution, which is a power series. There's your y1. And here's the other solution, y2. Now y2, we might say, is not a power series, or we could say, yeah, it's a power series. It just has one term in it. All the other terms, if you want to write it as an infinite set of terms, are just 0. So we say, okay, there's my other power series. I mean, it's silly to do that. Second solution is just x. And if you really wanted to check this, we could plug that into the original differential equation. If you go back and look at what the original differential equation looked like, take the derivative, take the second derivative, plug it into that, you're going to see that this is actually going to solve that differential equation. We could do the same thing with this. We could take the derivative of this, the second derivative of this, we could plug it in. You're only going to see that the first couple of terms are all going to end up canceling each other out and zero out, but that would then kind of show you that the whole thing is going to continue to do that. But nonetheless, it doesn't matter. We were told we're going to find two solutions. Here's one solution. Here's the other solution. y1, y2. So we solved it. All right, here's one more we're going to do with these ordinary points. So again, if you look at this one, the leading coefficient is 1. That's never equal to 0. So all x are ordinary. So I'm going to choose my center to be 0, because 0 is an ordinary point. So I'm going to say my solution is going to look like this, which is just some random power series centered at 0. We got to figure out what specific power series it's going to end up being. The derivative here, second derivative here, all the same as we've been doing. We're going to plug them in for the derivative and for y itself. So what am I going to get? I'm going to get the sum of n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2 minus 1 plus x times the sum of n equals 0 to infinity of c sub n x to the n equals 0. So just like the other ones, what we're going to have to do is we're going to have to take this piece out here and push it in, but since it's a binomial, this is going to have to distribute into here, and don't forget about this minus as well. So what we're going to get is we'll have the sum of n equals 2 to infinity of n minus 1 c sub n x to the n minus 2 minus this times 1, so the sum of n equals 0 to infinity of c sub n x to the n minus the sum of n equals 0 to infinity times the x. So if the x goes in, we get c sub n x to the n plus 1, because we have x to the n, x to the first, and that equals 0. Okay, now we're looking at, we got these three series. We're going to try and put all these three series together. So we'll first match up the powers on the x. So this one will be k equals n minus 2. This one will be k equals n, and this one will be k equals n plus 1. Telling me now n equals k plus 2. This one k equals n, and this one n equals k minus 1. All right, so what do we got next? We got the sum of k equals 0 to infinity of k plus 2 times k plus 1 c sub k plus 2 x to the k minus the sum of k equals 0 to infinity of c sub k x to the k minus the sum of k equals 1 to infinity of c sub k minus 1 x to the k equals 0. So now our x to the k's are all set up. So now we just got to do our indices. Well, highest one is a 1, so this has to go up by 1, this has to go up by 1. So we'll run one term out of here, run one term out of here. So the k equals 0 term is going to come out of this series, which will give me 2 times 1 c sub 2 x to the 0. And then the k equals 0 term is going to come out of this one, which will be minus, because don't forget the minus in front, minus c sub 0 x to the 0. And now the whole thing's ready to come together as one series, starting with 1. So we'll have this coefficient minus this coefficient minus this coefficient, all x to the k. So we'll have, what, k plus 2 times k plus 1, c sub k plus 2 minus c sub k minus c sub k minus 1 x to the k equals 0. Alright, so then what we need to do is we need to start looking at this. This is all for x to the 0, so we could write this as 2c2 minus c0 x to the 0 plus this whole deal. Now remember, all the coefficients are going to have to be 0, so this one will be 0. So that's going to tell me that 2c2 minus c0 has to equal 0. So c2 would be c0 over 2. So we get that. Then this has to equal 0. Well, if that equals 0, I could solve for c sub k plus 2, because that's the highest one. C sub k and c sub k minus 1 come before c sub k plus 2. So I would get, what, c sub k minus c sub k minus 1 all over k plus 2, k plus 1. That'll be for which k's? K's starting at 1, so 1, then 2, then 3, then 4. Alright. Now one little thing that's different here than any one we've done so far is that this term is defined in terms of 2 previous terms. We haven't really had that yet. But it can happen, so this is an example of that. Okay, so here's what we have. Also on the previous slide, I had a minus here. It should be a plus, because in the original summation it was a minus, so to move it to the other side it would actually be added. So I corrected that here when I rewrote it. Alright, so we got to generate some terms here. So let's start with k equals 1. K equals 1, we get c sub 3 to be c sub 1 plus c sub 0 over 3 times 2. Now I could leave that like that. Another way I could write it is c sub 1 over 2 times 3 plus c sub 0 over 2 times 3. I could split it apart. It all kind of depends on how this whole thing develops, whether you want to keep it together or whether you want to split it apart. So I'm just saying we could do either one. Let's keep going. K equals 2. I could say c sub 4 is equal to c sub 2 plus c sub 1 over, what was it, k of 2, so over 4 times 3. Remember, c sub 2 was c sub 0, so I could say c sub 0 over 2 plus c sub 1 over 4 times 3, which I could also write as c sub 0 over 2 times 3 times 4 plus c sub 1 over just 3 times 4. I could split this fraction apart and keep going and keep going and keep going. But honestly, I think this is going to be enough for us to have at least 4 terms in each series. Notice that every term is defined in terms of 2 previous terms, C1 and C0. So we really didn't have to go that far, and we already generated actually quite a bit. So what do we have? We assumed the solution was of the form y equals the sum of n equals 0 to infinity, c sub n, x to the n, which was really c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed plus c sub 4x to the 4th, etc. So we figured out that C2 equals C0 over 2, C3, C4, but we never said what C0 and C1 equal, so we'll just leave those. So C0 is C0, C1 is C1, C2 is C0 over 2, C3 is actually in terms of both C0 and C1, so it's C1 over 2 times 3 plus C0 over 2 times 3, and that's my x cubed. And then C4 is in terms of C0 and C1, so C0 over 2 times 3 times 4 plus C1 over 3 times 4, x to the fourth, and that'll just pattern to keep going. So if I distribute this x cubed into here and into here, same thing with the x to the fourth, and then I separate all my C0s and my C1s, what I'm going to get is, so we'll get C sub 0 times what? Well, if we pull the C sub 0 out of this first one, we're going to get 1. Then we're going to get 1 half x squared. Then we're going to have a C0 with an x cubed, so that'll be what? 1 over 2 times 3x cubed. And we have C sub 0 with the x to the fourth, so it's 1 over 2 times 3 times 4x to the fourth, and that'll just keep going. And if I do the same thing with the C1, I'll put it down here so I can fit it. I'll pull it out and you have an x. I'll have an x, and there's no x squared because the only thing with the x squared is C0, but I will have an x cubed. So that'll be 1 over 2 times 3x cubed. And then there's an x to the fourth, so 1 over 3 times 4, x to the fourth. And then there'll be an x to the fifth, I'm sure, but we didn't get that far, so we'll just keep going. And you see, again, we got our two solutions. Here, this one is one power series, and that's going to be your first solution, y1. Here's another solution. That's another power series. There's your y2. So we did get our general y equals c0 y1 plus c1 y2. And again, whether I call it c1 y1 or c2, doesn't really matter what I call this and this. But some constant times our first solution plus some constant times our second solution. And there are just two power series solutions. Again, not going to make you write it in summation notation if you left the answer like this and like this. We're all good. But sometimes this happens. Sometimes your recursive formula has one term written in terms of two previous terms instead of one previous term. And it's not really any different. It's not a big deal. It's just that every other term doesn't have a C1 in it. Almost every term will have a C1 in it. Same thing with the C0. But other than that, everything's pretty much the same. So, those are some of the basic examples of things that can happen when we're solving a differential equation centered at an ordinary point.